It is an honor for me to be the first one and open this symposium which gives us the opportunity to think or rethink about the role of plastics in photography and about the large portion of our photographic heritage bearing these plastic supports and the methods and decisions that we are taking to preserve it. I would like to dedicate this talk, although it's just a talk, to Peter Adelstein for all what I learned from him and from his readings. Okay. And although this is a talk centered on the technical aspect of plastic supports, I'm hoping to contribute to answer bigger questions, such as how plastics shape the history of photography, the technical history, the social history, and the art history, but also our own history as people from the 20th century. And why are the images bearing plastic supports so important? And what do we lose when we lose them? And what do we preserve when we preserve them? I would like to recall the challenges involved in the development of and manufacture of flexible and transparent photographic support, which period the development of highly sophisticated light-sensitive emulsions, and talk about the transition periods and the intensive research and innovation and trials involved in this period. This talk narrates the way in which the ideal properties, as Peter Adelstein mentioned in his writings, physical, mechanical, and chemical properties of transparent supports such as lightness, flexibility, low flammability, low shrinkage, toughness, stiffness, low moisture absorbance, dimensional stability, chemical stability, were eventually achieved by the photographic industry. And the first property that was achieved was lightweight, and it was achieved with celluloid, which required nitrating cellulose up to a 2.3 degree of substitution, which is between a D-nitrate and a 3-nitrate of cellulose. And nitration was sometimes inconsistent due to the irregularities such as the amorphous regions versus the crystalline regions in the cellulose fiber. So the addition of sulfuric acid improved the process. Sulfuric acid swallowed the fibers and facilitated the penetration of nitro groups, also reduced the reaction speed and allowed the production of a more uniform celluloid. After nitration was completed, all the acid had to be perfectly washed to avoid the retention of sulfuric acid. The nitrated cellulose was then threaded and rolled up. A 50% solution of camphor in alcohol was added, which increased the film flexibility up to 20%. Camphor separated the bonds between the molecules, changing the macrostructure of the threaded celluloid into a gel with no fibrous orientation. And camphor also reduced the explosiveness, but not the flammability of cellulose nitrate. John cardboard celluloid dry plates were cut sheets or slices, 1 of 100-inch thick from celluloid blocks, coated with a gelatin emulsion. Cardboard placed these sheets into frames where they were stretched down and fed into a forced air press. After a curing period of 6 weeks, the cellulose sheets were then treated to create like a matte surface to prevent halation, or like an anti-halo surface. Cardboard celluloid dry plates were very limited in size and thickness, and they were sold as flexible film, but they were really not very flexible. They were stiff and therefore unsuitable for roll film. So plastic supports really became very important after the introduction and the manufacture of rolls. And cellulose nitrate was tough but flexible, which made it ideal for this purpose. So by casting a film from a solution in alcohol, George Eastman was able to produce a thin, very flexible photographic support and started selling gelatin emulsion roll films in 1889. At the very beginning, the dope or the mix of cellulose nitrate was distributed over a 200 feet long platen with a hopper. Vents and radiators were used to evaporate the alcohol, the solvent. The photographic emulsion was then applied with a similar mechanism to the one that was used to distribute the dope. And when the emulsion was dry, the photographic film was detached from the platen and rolled up. But these films were limited in size and length, mostly in length. So the next, and maybe the most important and more important change was the casting of the film over a rotating cylinder in 1898. The dope, in this case, the dope was poured over 9 feet of a very big cylinder. And as the cylinder rotated, the solvent evaporated. And after one revolution, the film was detached from the cylinder. So it could be made in a continuous way. And I think the impact of this machine for photography was comparable to the impact of the Fourdrinier machine for the history of paper. And one of the challenges is that the gelatin emulsion did not adhere well to the plastic support, so a subbing layer formulated with gelatin in water and a water-soluble solvent, such as ethanol or acetone, and a small amount of cellulose nitrate was applied to the support before coating it with the gelatin emulsion. Another improvement was the anti-curl layer. Because of the dimensional changes of the gelatin binder, derived from changes in the moisture content of the gelatin, resulted in curling and buckling of the photographic film. So starting in 1903, the gelatin layer, called anti-curl, was applied to the back of the support to counteract the tension exerted by the gelatin. This layer was applied over a subbing layer similar to the one that was used on the front. And cellulose nitrate roll film really changed the practice of photography. Its impact was maybe greater than any other photographic process. It changed the medium of photography, making it accessible to everyone, and gave birth to another medium, cinematography. And this is the kinetoscope, with all what cinematography brought to the world. And cellulose nitrate was really perfect. But as you know, it had a few shortcomings, like its flammability and low chemical stability. But cellulose nitrate, was used as a model for the creation of other plastics. So the alternative plastic was cellulose acetate, the result of the esterification of cellulose with acetic acid and anhydrous acetic, which was produced since 1897. But it took nearly 5 decades to produce photographic supports with the more dimensional stable cellulose triacetate, the fully esterified polymer. And cellulose triacetate could not be, that's because cellulose triacetate could not be made in different degrees, cellulose acetate could not be made in different degrees of acetylation. And only cellulose triacetate was available since the beginning, but it could not be it was not soluble in any of the solvents that were available at that time to cast the film. So in 1905, a process was introduced to partially hydrolyze cellulose triacetate to obtain acetates of lower acetyl content between 2 and 2.5 acetyl groups per glucose unit, which were soluble in the solvents available at that time. Cellulose acetates, these cellulose acetates were referred to as secondary acetates, diacetate, or acetone-soluble acetate. And they had between 38 and 41 acetyl content as compared with the 44.8 acetyl content of cellulose triacetate. So, and this hydrolysis step also removed combined sulfuric acid. Cellulose diacetates were hygroscopic and dimensionally unstable and became brittle over time. And other cellulose derivatives such as viscose and ethyl cellulose were investigated, but cellulose diacetate remained like the best option. So in 1910, Kodak started selling motion picture film in smaller formats or non-professional formats on acetate vase and pâté flares in 1912. Its performance was acceptable or satisfactory for home movies, such as the 16 millimeter home movie film introduced in the 20s. And cellulose diacetate was used as support for most film formats during the 30s and the 40s, except for motion picture film. And Kodak introduced better secondary cellulose acetates by using propionic and butyric acid along with anhydride acetic in the esterification reaction. The result was cellulose acetate propionate containing both acetyl and propionyl groups used for roll film and on home movie format films at 16 millimeters and such as 16 millimeters and 8 millimeters. And cellulose acetate butyrate containing acetyl and butyryl groups used for sheet films, X-ray and aerial film, and graphic art film. However, no one of these acetates had the moisture resistance, stiffness, and mechanical strength required for professional motion picture film. So, in 1944, between 1944 and 1948, and just prior to the introduction of cellulose triacetate, Kodak was able to produce cellulose acetate with a higher acetyl content for 35 millimeters duplicating positive film. This plastic, called high acetyl content, contained between 42.5 and 44% of acetyl content. And it has the solubility of secondary acetate, but the strength, stiffness, and dimensional stability properties of cellulose triacetate. Adding up to 20%, between 20 and 30% of cellulose nitrate to the cellulose acetate polymer was another option to make a safety film with better mechanical properties than cellulose diacetate. Methylene chloride, the best solvent for casting cellulose triacetate film, was available in large quantities or in a lower cost after World War II. So in 1948, Kodak introduced cellulose triacetate film for all roll formats, including motion picture film, triphenyl phosphate, or dimethoxyethyl phthalate were added as plasticizer. And triphenyl phosphate also acted as a flame retardant. The 7-layer was made with dilute dilution of cellulose, either cellulose nitrate or cellulose diacetate with gelatin. Initial problems in the manufacture of, and this cellulose triacetate, as you know, it was used until recently. Initial problems in the manufacture of cellulose triacetate, such as this lower rate of the machine production and the loss of solvent during casting were overcome by adding small quantities of other solvents to the methylene chloride. And cellulose triacetate had to say that it required solvent containing dioxane for solvent splicing for motion picture film. Dimensional chemical stability. Polyester refers to polyethylene terephthalate introduced by DuPont in 1955 for the graphic art films. But there was also another polyester called polyethylene naphthalene, which was used for the Advantix photographic system from 1996 up to 2004. But we normally refer to polyester as to polyethylene terephthalate. It was introduced as a photographic support for film that required very high dimensional stability, such as for aerial film and graphic art film. But before the introduction of polyethylene or polyester, several polymers were investigated with the aim of producing a less moisture absorbent and therefore more dimensional stable support than cellulose acetates. Among these polymers were polyvinyl chloride with vinyl acetate and polyestyrene. The first one was used between 1945 and 1955 for graphic art film, but it was not, its dimensional stability was only temporary. It was very stretchy and difficult to manufacture, and it required a calendaring process which left a matte surface. Polystyrene sheet was extruded, not cast, from a melt. That is, the plastic without solvent squeezed between heated rollers to form a sheet, and it was subject to biaxial orientations the same way as polyester. It was used in 1954 for graphic art films by Kodak. Its moisture resistance was not as good as that of polyester. And another type of polyester, polycarbonate, was introduced by ACFA in 1957 and was used by ANSCO for graphic art film and aerial film, but this one did not have the stiffness of polyester and was more expensive. As with polystyrene, polyester sheet needed to change the entire technology because it is extruded from a melt and stretched in both directions. Several thermal and mechanical treatments are required to promote the formation of semi-crystalline, not amorphous polymer. Being hydrophobic, polyester has no functional groups to adhere the gelatin motion, which is hydrophilic. So the surface of polyester support has to turn hydrophilic with a corona or plasma treatment, or by coating it with a special subbing layer that has carboxylic acid groups, which may be applied after a first or axillary layer. And this is manufactured process. Polyester is not only tough, but it is also thermally, dimensionally, and chemically stable. And it gradually replaced cellulose triacetate as support for sheet film, and more recently for motion picture film. But it's not like really ideal, or what we say, like perfect, because it has some disadvantages for motion picture film. It is too tough and sometimes may damage the machinery when trouble occurs. It cannot be solvent spliced, so it requires a dielectric sealing or adhesive tape to edit film. And its core set properties are not as good as those of cellulose triacetate, and that is precisely because polyester does not absorb any moisture and cannot be relaxed and reshaped. Also, polyester support is more susceptible to scratching and requires greater protection from static discharges, which may fog photographic emulsion. And to conclude, plastics introduce profound changes in the practice of photography, in the use and distribution of images, and therefore in the shaping of visual literacy. But the problem with plastics is that they have a bad reputation. They are associated with the temporary and the disposable. They do not age well. Some of them are dangerous, and photographs on plastic support are sometimes neglected. And because their value as objects is not clear to everyone after the content has been transferred to another support. These photographs are in large quantities and not really readily accessible. And when they are very well preserved in cold storage, sometimes they become less accessible and maybe more prone to be forgotten. But cold storage should not be regarded as the end of a story or a way to bury a problem, but as a means of preserving a story still to be told. And can we think in the future, maybe these images will be considered the incunabula of mass media? Transition periods are characterized by changes in the material. Constant improvements introduced in the manufacture of plastic supports, and even small changes made by manufacturers to avoid patent infringement or to lead the market suggest that the variety of plastic supports might be wider than we tend to think. And the behavior of this plastic will not always be predictable. Thank you very much.